Okay.
Okay.
And then you're gonna
Did we
share
set the camera and the
Yes.
audio yet?
Yep.
Camera is set.
and then drag.
Excellent. I can introduce.
Okay, great.
Hello, everyone. Xiang Li is a fifth-year PhD student from Stanford, advised by Professor Percy Lee.
Exactly.
If anyone's on Zoom with okay. She's advised by Professor Percy Liang and Professor Tatsunori Hashimoto. She's interested in controllable and steerable language models and constructing new evaluation frameworks for language models. Previously, Lisa received the Best Paper Award at EMNLP for her work specializing word embeddings by information bottleneck. Please welcome her into giving her talks on enhancing evaluation coverage.
Hi everyone, my name is Lisa. Today I'll talk about enhancing evaluation coverage and validation with language models. So language models are good at following a diverse set of instructions, and they are really general purpose. So if I ask them for some touring suggestions in New York City, ChatGPT is gonna give me like top 3 places to visit, which is pretty reasonable. I can also ask it to play a game of 22 with me. Basically, given 4 numbers, it's trying to form the number 22 out of this. And ChatGPT is able to give me a completion with some explanations. Last but not least, I can ask ChatGPT to function as a language tutor, and it can teach me some French. So while having a general purpose language model is really empowering and helpful, it is exactly because they are general purpose that makes evaluation really challenging. So to understand this better, let's take a step back and remember how evaluation worked before. So previously, in the old paradigm, we would have specialized model. Suppose that we want to train a knowledge-intensive question answering model, we would first figure out some knowledge-intensive data sets like natural questions used to train the model. And then to evaluate this, we would evaluate them on the associated test set. For example, natural question test set or some other knowledge-intensive distribution like Squad or Trivia QA. Nowadays, people would train a general purpose foundation model on very broad internet data like Common Crawl. And then once we have the foundation model, we'll query it using different instructions or different prompts to conduct a diverse set of tasks. So essentially, to evaluate these general purpose models, we can ask anything, and anything in terms of evaluation becomes fair game. So as we showed before, we can evaluate the models on itinerary generation, we can evaluate it on language tutoring skill, etc. Given that anything is fair game, what tasks should we actually evaluate the language models on? More specifically, what distribution should we use to query the language models? That's the first question we'll discuss in this talk. And even if we do know what tasks to evaluate the language models on, for example, here's the little angel telling us that we should evaluate language models on knowledge about cooking recipes. The output of the language model can still be very free-form and open-ended. And for some tasks, the output might also be very high entropy. Therefore, judging the correctness becomes a lot harder because there is no single correct answer when we're evaluating these language models. For example, there could be multiple ways of cooking Kung Pao chicken. Some recipe may say that you should add 2 teaspoons of sugar, but like this little girl's mom would say, well, maybe you should add 3. So is the recipe correct? Maybe it is. Maybe the small delta in sugar amount doesn't really matter, but maybe it does. So this is exactly what makes judging the model responses pretty hard because there is no single standard. Given 2 evaluation problems, problem 1 is what task do we evaluate the language models on, and problem 2 is how do we validate this model responses? These 2 problems will persist into the future because as the language model gets stronger and stronger, it will be able to do even more tasks. So problem 1 becomes more important. Moreover, as the models becomes more capable, they can probably provide us some reasonable sounding answers to pretty hard problems that are even harder to validate. And maybe you have to be a domain expert in order to validate whether the answer is correct or not. So it's pretty important to figure out the solution to those 2 problems. First, let's think about problem 1. What tasks should we use to evaluate the language models? One common practice that people typically take is to take the union of existing datasets for evaluation, including GSMA-K, MMLU, and Trivia QA, etc. However, the existing datasets cannot really cover the vast space of potential use cases or desired domains that you actually want to apply these models. So a natural proposal is maybe let's just add more datasets. We know that building dataset is very costly, and running all the popular models on the newly built dataset can also be pretty expensive. So we want to carefully consider the problem of like, what is the next dataset that's actually worth building, that can add most information to our existing set. For example, QA has been a really popular subtask or subfield in NLP. One of the first QA dataset is Squad. And researchers sometimes find Squad to be not good enough because it covers Wikipedia domain. So it fails to cover other domains like news or trivia. So they come up with these two new datasets. Similarly, Squad questions is based on crowdsourcing. So it's not naturally occurring, and therefore people come up with natural questions to try to complement Squad and make it better. So here is a toy sketch of what would happen if we actually evaluate on all the QA benchmarks or the QA datasets. This dataset leads to results that are roughly similar to each other. They kind of induce very similar model rankings. They have like rank correlation pretty close to 1. Now these datasets are just kind of revealing redundant information as each other. So whenever we're adding a new dataset, it's adding very little new information. So people who are considering using the dataset might just say, well, they look pretty similar in terms of performance. Why should we use the new one? We'll just keep using Squad. So the above phenomenon suggests that, well, sometimes our intuition for building a new dataset is wrong. We thought that we add a new dataset that's supposed to review some new capabilities, review some new weaknesses in models, but turns out they just like kind of reinforce each other's conclusion. We thought we've built something new, but it just kind of confirms patterns. And specifically, it just confirms the first principal components of existing datasets. So we can see that the first PC kind of explain 80% of total variations in terms of like model performance. And the first 3 principal components combined is able to explain up to 97% of all the variance in model performance. So also because PC1 tends to be highly correlated with scale, this is a little bit sad because it means that by adding new dataset, all we discovered is like, this model is large. It's kind of revealing the same information that scale could have told us. So we want to break out of this loop and design new dataset that doesn't conform with existing patterns, but instead we want to actively look for benchmarks that reveal interesting information.
So the PCA is from just QA datasets or on like all the datasets?
Oh, here this is like kind of the more modern set, like GSMVK, MMLU, like yeah, math, coding, etc. Cool. So overall, we want to construct a new dataset more scientifically, relying on quantitative metrics and not just intuition. Towards this goal, we propose AutoBencher, which is a declarative framing for benchmark construction. So there are 2 steps. The first one is that we declare a few desideratas that we want to care about, like salient, novelty, difficulty, and then we cast dataset construction as an optimization problem to optimize for the dataset to satisfy the desideratas. Now let's move on to the second problem. How do we validate model responses? The classic approach of benchmarking is to collect all the correct answers or to collect their rubrics, judging correctness. This is pretty reliable, but it's really slow and costly. Another popular approach recently is to use language model as judge. The problem is that it is not very reliable because it relies on language model, but it's really cheap and fast. So the question is there something that would fall in between that could be both reliable and also cheap? We know that this is kind of wishful thinking because we are trying to get everything for free, to get everything at the same time for free. But maybe we can solve a subset of evaluation problem. And one attempt is to use consistency as a judging criteria. Yeah.
So just to understand where you're headed, so you found this PCA structure, so you want to go to a nonlinear structure and avoid PCA. That would be a natural conclusion. You have to go out of this subset.
Yeah. Well, I guess we're trying to find things that are still linear. Well, I feel like the thing that I'm trying to get at with the first problem is that we're not evaluating on the same on the right subset or on the right distribution over input. Because if we find some distribution over inputs that actually is able to reveal something that's like even pretty novel in terms of just a linear structure. So it's more
So
like,
you're still hoping
yeah.
to search within the subspace.
yeah, we are still searching the linear subspace, but we are just trying to change the input distribution such that even in the linear subspace, it's gonna give us something different. Cool. So here's an example of using consistency to judge model responses. I asked ChatGPT to give me a quote about consistency, and it generates a plausible sounding quote. However, in the next turn of the conversation, it hedges and gives me something that's contradictory. So consistency is essentially an agreement test. So we can conclude that the information from ChatGPT 3.5 is inconsistent even without knowing whether the code is true or not true. We know that consistency can be checked without using ground truth, therefore it's pretty cheap and fast, and we don't really need to collect ground truth information for it. Also, when we detect an instance of inconsistency, we know that something is definitely incorrect. But there shouldn't be any free lunch. So what does consistency sacrifice? Turns out it trades off precision with recall. So if a model response is consistent with each other, it doesn't really say anything about correctness. For example, if two models both say that NYC is the capital of New York State, then they are consistent, but they are both wrong. Now we'll compare the error detection pattern using consistency test and using language model as judge, side by side. For language model as judge, it achieves neither perfect precision nor perfect recall. Whereas for consistency, we know that precision is kind of guaranteed, but we're sacrificing recall. So overall, we'd say that consistency has more controlled failure pattern because we know that it's going to miss recall. Whereas for language model as judge, it's kind of uncontrollable that it can fail arbitrarily. So this summarizes, yeah.
So by consistency, you don't just mean that the answers are, it'd be inconsistent, not just that the answers are different, but if they're mutually inconsistent.
Yeah. It doesn't mean different, it means contradictory. I feel like they can be different, they can have like support different things, but as long as they don't say stuff that are, especially for factual things, if it's not contradictory to each other. So this roughly summarizes the trade-off. For consistency, we can get reliable judgment. It's cheap and fast, but we sacrifice its recall for it because we can only get signal when things are inconsistent. So this scale roughly measures the level of language model involvement. If it's too much, then it's not that reliable. If it's too little, then it's not very scalable. We are trying to find some middle ground where we use language model plus some carefully designed scaffolding to make it relatively reliable and also relatively scalable. So here's the roadmap of the talk. I'll first discuss AutoBencher for generating inputs. This is the paper that we'll cover. So to determine some desideratas of evaluation datasets, let's start by analyzing some existing datasets. We include MMLU, GSM8K, ARC, and TruthfulQA. So looking at their descriptions, the benchmarks all evaluate salient and important topics or skills such as math, reasoning, knowledge. The salience of the dataset is an important consideration for benchmark designers. Then let's look at the difficulty of these datasets. Specifically, we look at the best model's accuracy on each dataset. We find that some datasets are more challenging, achieves an overall lower accuracy, like TruthfulQA, whereas some other datasets are mostly saturated, like ARC. So this leads to another important desiderata, which is difficulty. Designers want their datasets to be sufficiently difficult so that it's able to distinguish performance among existing models, and also it's able to keep track of model progress for future stronger models. One caveat is that you don't want your dataset to be too difficult. Like if the dataset contains questions like to prove P equals to NP or not, then it can't really distinguish model performance because every model is going to get 0. And more recently, people have discovered that existing datasets are highly correlated with one another, meaning that they reveal redundant information and confirms conclusion from each other, as we just talked about. So here, this is a rough sketch of what we mean by redundant information, that each dataset roughly have the same winners.
Question?
Yeah.
Is that conclusion right? I mean, there's also the inherent capability and that's possible. Is that the source of the main correlation?
Yeah, I mean,
Problem with it?
Sure, there are definitely like basically some important like underlying capabilities in models like reasoning skills that kind of is the latent variable that controls the performance on all the reasoning related data sets. But I guess
Isn't that even the main source of the correlation between that?
yeah, that's indeed the main source of correlation. But I feel like for a particular like benchmarking paradigm that we want to consider, like for example, for if we care about knowledge intensive stuff, maybe like we want some form of novelty. Overall, it's kind of like uninteresting to keep adding one more data set that will measure the same thing. So we are trying to find maybe like some different input distribution that will actually recover some different performance patterns or some different rankings. Maybe it entails that it no longer measures the first principal components, or maybe it doesn't exactly measure the underlying capabilities. Maybe there are like, I mean, there could be a few underlying capabilities that are dominant, whereas here we are trying to find kind of the residual thing that complements the major underlying directions.
No, so for instance, you know, you said the performance is predicted by this top singular vector.
Yeah.
Presumably what that gives you is a ranking.
Yeah.
Thank you.
Yeah, so I guess we're trying to find things that are complementing to the existing paradigm by like finding different input distribution that are also similarly meaningful, that looks pretty important, that breaks the trend.
Okay.
So that is like additional information. Yeah, ideally, this is something that we're looking forward to. It would be informative and interesting to have different data sets reveal different insights about model behavior like this, where different data sets would have different winners. For example, if the Mistral model achieves unexpectedly high performance compared with its regular ranking, it means that we've discovered some unexpected strength of the Mistral model. And if Gemini achieves a much worse accuracy compared with its regular ranking, then it means that we've discovered some unexpected weaknesses in Gemini, maybe such as knowledge gap, such as reasoning weaknesses. So roughly, this is the thing that we're looking for by optimizing for novelty. Given that we want to construct a data set that's salient, difficult, and novel, we can write this as an optimization objective. And then there are two steps we need to do. First one is to operationalize each metric. And second is to solve this optimization problem with the design metrics. So before we delve into the detail of the metrics, let's first go through some quick notations. Let's C be a dataset description or a dataset topic. We define DC as the set of QA pairs that evaluate mastery of C. For example, C could be compute the second derivative of polynomials. It could be compute joint probability of two dependent events. It could be like major events and timeline in World War II, or it could be like economic impact of COVID-19, etc. And we denote accuracy of a model M on a benchmark as the accuracy of language model, comma benchmark or dataset. And then we define the accuracy vector of a data set by just concatenating the accuracies of all the test taker models on this data set. And in this work, we focus on optimizing over the data set description C, and we assume that we have a fixed data set generator condition on the description. So in other words, we don't directly optimize over questions. We don't optimize over individual questions to avoid overfitting. And instead, we optimize over the dataset description so that we can find systematic patterns of failures or success.
Natural language description.
Yeah, natural language descriptions. So salience measures when we're operationalizing salience, it measures the importance of a topic C. So basically, we assume salience to be a binary metric. Here are some examples. If we ask questions about 2024 Summer Olympics, well, for example, we can base on the number of Wikipedia page views to judge salience of a topic. Here it has 4 million views, so it's pretty salient. Whereas for some maybe small town in Minnesota, it only has 27 views, so it's less salient comparatively. We can also train a model to approximate human preference of salience. A benchmark's difficulty is basically determined directly by the model's error rate. So ideally, a benchmark should leave sufficient headroom for future improvements. And we formalize difficulty basically by taking the accuracy vector and look at the best performing model's accuracy, and then compute the remaining gap between the best model accuracy and 1. So novelty measures how much new information a data set is revealing that is not already shown by existing data sets. Therefore, we formalize novelty to measure predictability of the model's accuracy on the new data set based on accuracy vectors from existing data sets. here's a very simple example. Given two models, LM1 and LM2, and one data set, 1, we plot their respective accuracy of 0.6 and 0.3. And now we have a data set 2 with language model 1 accuracy of 0.8 and language model 2 accuracy of 0.4. And since the accuracy vector of dataset 2 is spanned by the accuracy vector of dataset 1, the performance of dataset 2 is highly predictable, so it is not very novel. Now consider a different dataset 2 with language model 1 accuracy of 0.4 and language model 2 accuracy of 0.2. Since the accuracy vector of dataset 2 is no longer spanned by the previous accuracy vector, the performance on the new dataset is not very predictable, and therefore it will have a high novelty. So overall, a novel dataset entails that the accuracy vector is not predictable or is not spanned by the existing accuracy vectors. Now let's consider, let's generalize this to more than 2 datasets and more than 2 models. So we'll first train a linear regression to predict the accuracy on the new dataset VC from existing datasets, from existing sets of accuracy vectors. And then we will measure the goodness of the prediction based on the Spearman correlation. And finally, we report novelty as 1 minus the Spearman correlation between the prediction V hat and the ground truth VC. Yeah.
Just do this like just by using like low rank or just like the rank of the subspace?
By rank of the sub, you mean to do the prediction based on the rank of the subspace?
Yeah, to measure predictability as like at the beginning you mentioned, you basically the issue you had at the beginning was that you had one you had one component and it was dominant, so you basically had all the data you've seen before, all the benchmarks people have been building, they're all low rank, they all have rank.
Yeah, right.
And so what you want is like that to be high rank.
Yeah, right, exactly.
And so could you just measure novelty as
the rank?
The rank.
I guess, yeah, that makes sense. But like, so typically we're measuring accuracy of the added benchmark. So mostly, I guess, well, if we formalize it in rank, then we would care about like the rank of the new matrix is 1 additional column than the rank of the matrix before. With 1 fewer column.
You need multiple data sets.
Yeah. And basically, we use separability to complement novelty. Since we measure novelty using rank correlation, we don't really want the data set to be trivially novel because all the accuracies are similar to each other. As in this example, the first column, data set 1, is not very separable because all the data sets are pretty similar to each other. All the accuracies are pretty similar to each other. So if we add a little bit of noise, maybe if we bootstrap or subsample the data set, the ranking will change by a lot. Whereas in the latter case, we have the data set 2 being more separable because the accuracies are more spread apart. So we use separability as a regularization term when we are operationalizing the objective. So combining these metrics, we used like we can write down the overall objective function. Our goal is to find a sufficiently salient data set description such that it is novel, difficult, and separable. We propose to,
Do we care so much about the difficulty if it's, we already know that it's separable? So if it's.
If it's already separable, then it's probably kind of, I mean, at least it's difficult for some data set, for some model and not difficult for the other.
Right, like it doesn't matter so much if it's like a good level of difficulty, if it's just all the models are doing exactly the same anyway. Like I thought, one of the points of having it be a moderate level of difficulty would be that you have separability.
I mean, well, yeah, even if you have separability, like, but if the best model is achieving 100% accuracy, it may still not be a very good data set because you can't imagine that next month some new data set, some new models gonna come out.
It's about future models.
Yeah, it's about future models. Yeah.
In terms of the difficulty metric, what about like some tasks that like models can initially get a very high score, but it's just hard to improve? And some of the tasks that the models can get a really low score, that means like higher level of difficulty, but the score can be easily improved with say like synthetic data and things like that.
I guess for now we didn't really, at least for the scope of this project, we didn't really care about like downstream improvements or how easy it is to bridge the gap. But I mean, from a high level, I feel like the goal of like AutoBencher is that it's able to find some unexpected weaknesses, and maybe we kind of encourage that maybe model developers to go to like they become aware of this weakness and then they will go back and train the model to fix it. So I guess being fixable could be a good thing. So I guess here's a naive implementation of how we are going to do the search. We will first use the language model to propose a set of topics or descriptions. And for each topic, we will generate a data set of QA pairs. And then we will evaluate a set of test taker models on this generated data set to get their accuracy vectors and compute their respective objective functions. And finally, we'll select the top data set according to the objective. So this naive design has several problems. First of all, the topics proposed by the language model might be too easy. For example, if the topic is like, such as important events in World War II, then it might still be like, the topics might be too easy so that the resulting thing is no longer very novel. Another problem is that the generated question might also be too easy if we're just purely generating from the data set from a language model. It might just ask questions that all the test taker models are able to answer correctly, like who's the first president in the United States. And also, the answers may not be correct because it is model generated. So to address these problems about generating easy questions and potentially incorrect answers, we augment AutoBencher with privileged information. So we call this privileged information because it's only accessible to the question generation model, which is used to generate the QA pairs, and the same information is not really accessible to the test taker models. So this asymmetry of information makes the problem a lot simpler for the question creator model, allowing it to create questions that are more difficult than possible with its base capabilities. So in order to create, for example, in order to create knowledge-intensive questions on a given topic, we first retrieve relevant Wikipedia articles, and then we prompt the language model to generate QA pairs conditioned on the retrieved articles. For multilingual tasks, we augment the language model. Yeah.
So that line is in Wikipedia. Then what sense is it privileged?
I guess it's privileged because, I mean, when the model is generating the questions, it can see the Wikipedia articles in context. Whereas for the test taker models, we assume that it's not doing any RAG. We assume that it's not doing any retrieval augmentation. So in that case, it kind of have to answer this knowledge in a closed book format.
So this assumes that a model that is memorized Wikipedia is actually better. What sense is this?
Sure, I mean, like all the models nowadays probably have already trained on Wikipedia.
Yeah, of course.
Yeah, but
like this, like word for word.
Yeah. I mean, well, there could be both word for word memorization. Sometimes, I mean, empirically, there's a performance gap between like if you first ask the model to regurgitate like the Wikipedia articles and then answer the question, versus if you ask the model to directly answer the question. So there's a big performance gap between these two cases as well. Sometimes, like even if the model is trained on Wikipedia at pre-training time, it still couldn't really answer any of the Wikipedia questions, even if it might be able to memorize the entire articles verbatim.
I mean, I'm not sure what such a model is, but I mean, yeah.
Okay, I guess.
More compelling example.
Yeah. Okay. I guess, okay, for multilingual tasks, we augment the language model with a translation system. So since model tends to have better reasoning capabilities in English than in other languages, we basically take the English QA pairs and then take a translation system to translate the question and answer pairs to the target language. And for math domain, we augment AutoBencher model with Python math libraries such as SymPy, SciPy, or NumPy. And then we prompt the language model to generate questions along with the respective Python codes to solve the problem. And then we use the execution result as the silver answer. So this is the full AutoBencher algorithm. Given a domain such as history, AutoBencher first uses a language model to propose a few topics, such as timeline in space race, economic impact of World War II, etc. And then condition on each description, it will use a language model with privileged information to generate a data set. And then we evaluate the test taker models on these data sets to compute their respective scores for each desiderata. And then we gather a trajectory of topic, difficulty scores to inform the next iteration of AutoBencher proposal. So for the next iteration, when we are proposing the new topics, we use this trajectory to inform the language model about what topics are more likely to be difficult for the test taker models. And then the language model will propose new topics. It can steer towards the topics that are more likely to be difficult. For example, empirically, this is what happened. Like previously, history of mathematics is pretty hard. So it kind of come up with something similar to the history of mathematics, like history of education. Previously, like economic impact of World War II is pretty simple. So to make this category harder, it added it to be like maybe some finer grained notion of some finer grained category like Canada involvement during World War II. So we construct the data set and score them respectively and add the new results back to our search trajectory. For the next iteration, we keep doing this. And now the proposal language model has richer information about what topics are likely to be hard for the test taker models. So it makes better topic proposals. And then we use the language model to construct and score the data set and accumulate more history to the trajectory. And we repeat this until we run out of budget.
What's the proposal algorithm?
What's the proposal algorithm? It's implemented by prompting a language model with like in context learning examples of like topic, comma, difficulty.
So it's presumably finding adjacent topics.
Yeah, it's basically there are like two ways of optimizing it. Empirically, we observe that like, well, if it already has a topic that's pretty difficult, it will try to like kind of look around the neighborhood of that topic to kind of like extend it a little bit. Whereas if it sees something that's very simple, it might try to refine it to be more difficult by asking harder questions or more specific questions within that category. So for example, I mean, in the case of math, like to begin with, if you have a set of things like arithmetic, like with addition, and then it's pretty easy, then like maybe the next iteration of proposal, it might ask questions like arithmetic of like 3-digit numbers or something. So finally, we gather all the topics and their scores, and then we choose the highest scoring one, the highest scoring data set according to our objective. So here are some results of AutoBencher constructed data set. We plot difficulty, novelty, and separability as the 3 metrics that we optimize for. The green bar is AutoBencher. The blue bar is human written data set like MMLU or math data set. And we find that overall, AutoBencher outperforms human written data sets by generating data sets that's more novel and more separable and more difficult. I guess one concern about this model generated data set is their correctness and whether the question they ask are meaningful enough. So previously we mentioned privileged information can improve data set quality by making the answer more correct and by asking more difficult questions. But to further validate this point, we conduct human study to verify the correctness of the AutoBencher generated data set. So we confirm that this is the error rate in AutoBencher. And then on average for a human generated data set, the error rate is around 5%. And we find that AutoBencher is able to kind of achieve a similar overall error rate compared with a human generated benchmark. And we also ask Mechanical Turkers to provide salience labels for each AutoBencher questions, just to make sure that the questions are meaningful and important. And we confirm that AutoBencher datasets achieve a similar salience score compared with human-generated benchmarks like MMLU. So we basically ask them to rate salience on a Likert score of like not salient, low salience, medium, high, etc.
What information were they given for them to judge that it's salient?
I guess it's mostly just like, well, we provide some prompt about letting them judge what's the implication of this question of like, do they think that they are likely to ask this question? Do they think that like, well, general public might be interested in knowing the answer to this question? So it's kind of a subjective thing in terms of judging salience. I guess like it's kind of highly disputed because like something can be salient to one person, but less salient to the other person. And overall,
no, I'm very worried about that. Like, you know, if you just give them a passage of Wikipedia, they say, sure, it's in there, so it's salient.
Oh, no, we didn't really give them Wikipedia passages. We just give them the question directly. And then they look at the question and then judge whether it's salient or not.
But they wouldn't know about the details of the Sputnik program. Who are these people?
I guess, well, that's a great question. I guess, well, the people are like Mechanical Turkers online. I guess we ask the question mostly to, for example, for some econ questions, like, well, if the question is like, what's the outcome of inflation? Like, what's the impact to like real estate price due to inflation? Like it might just, even without any grounding, it might just sound like a pretty important topic or pretty important question. Whereas, yeah.
But your example.
Okay.
Is there a question, the previous part, are you talking about the correctness and you use privilege information to generate a question? Is that all the question you generate use privileged information or some of them are using it?
I think all of it is using privileged information.
And for those questions, I assume like, for example, if you, in the future language model has RAG or Python or Python, like the that is gonna immediately show like 100% accurate for your task?
I mean, sure, maybe. I mean, well, for example, here, like it also, I mean, maybe it's not gonna exactly achieve 100% accuracy. For example, like here, it still has like one layer of advantage above RAG because right now, like it doesn't even need to do retrieval. It's more like condition on the passage. I'm extracting QA pairs. Whereas if given a question, you have to go find a passage, you might suffer some recall error. You might suffer a little bit of like retrieval error. And then, so that's maybe the little delta, but it's probably definitely less salient or less obvious of a gap than if you ask one model to answer a question open book versus closed book. Yeah.
I wonder, like for calculating or like how are you using MMLU as the benchmark for like comparing methods? Because MMLU itself has some limitations. In this distribution, like all of the subjects are not evenly distributed. Like some subjects like moral scenarios or like some are global trivia. Those stuff much sense in terms of.
Yeah, we try to remove the the MMLU questions that are very scenario based, that like involves reading a long article and then answer the questions.
Gotcha.
Yeah.
So
Yeah, we use a subset of some tasks that I think is more salient than the others. Okay, so we spent a lot of time discussing the importance of a novel data set. And here, overall, here's the practical implication of what we mean by finding novel data set. So for example, we can use novelty to find unexpected weaknesses of generally strong model, like Gemini. Here, like we find that Gemini is bad at answering questions about Fordism, which is a pretty important economic concept. And we also find that some unexpected strength in relatively weak models like OpenAGI is only 7 billion parameters, but it's achieving pretty high quality answers when you ask it questions about COVID-19. So
Gemini Pro 1.5.
I think it's Gemini Pro 1.0.
Oh, that was a 7 TB model. Shouldn't be
Okay.
compared to.
Yeah. I guess right now, I guess I'm like comparing less about model scale, but just overall, like previously, it's like maybe around rank six in the general patterns of models.
Question.
Yeah.
Does it matter which model you use throughout the entire process? So if you use the same model to generate all the QA pairs, all the judgments to construct your data set, would that give an advantage to when you end up actually evaluating this model on the data set? Or like I was wondering if you have any study on that.
Yeah, I feel like I mean, I've tried using Cloud and using GPT-4 as the proposal distribution. I feel like it doesn't make a big difference because the question generation pipeline relies a lot on the privileged information. So basically, the privileged information mostly determines roughly what questions you're supposed to ask. It's not really just the model itself. So it doesn't really give unfair advantage to the respective models in the family. For example, most of the experiments done in the paper is using GPT-4 Turbo to generate questions. However, like Cloud 3 tends to always be the winner in many cases. Okay, so to conclude the first section, we propose a declarative framing for dataset construction, and we execute this by casting dataset construction as an optimization problem. So now we'll move on to quickly talk about consistency for checking model outputs. This is the paper that we'll discuss. We focus on a subcategory of consistency that we call generator-validator consistency. Essentially, we ask the same language model to perform a generation task and a validation task, and check whether the outcome of these two agrees with each other or not. For example, given the question about consequences of swallowing a watermelon seed, for the generation task, we just query like this: what's the consequence of swallowing a watermelon seed? And we pass it through the model to get the output. You will grow a watermelon seed. And then for the validation task, we take the generator response and convert it to a validation query. will you grow a watermelon seed if you swallow, will you grow a watermelon if you swallow the seed? And ask the model to output a binary value of yes or no. And the model says no. Then we judge the consistency between the generator and the validator response. And since the two responses are contradictory to each other, we label this as inconsistent. The idea of checking for agreement between the generator and the validator responses is quite straightforward. The key question here is, how do we construct the generator and the validator query so that it's not a very gameable metric? Here's a naive design. For the generator query, we ask the model to provide a correct response to some question. And then for the validator query, we ask it to judge whether the response is correct or not. However, this design is a little bit problematic because if we have a trivial validator that always answers yes to the validator question, regardless of whatever the generator response is, then this then a perfect GB consistency will be achieved trivially. So this is actually a real problem in llama models. For example, llama models tend to have this bias towards answering yes to binary questions or towards answering true. So we address this problem by injecting randomness to the generator and validator queries so that GB consistency is not a very gameable metric. So to insert randomness to the generator query, we randomly sample to query for a correct or an incorrect response. For example, in the style transfer task, where the goal is to rewrite a sentence to be more humorous, we can design the generator query to be rewrite the sentence to be more humorous or to be less humorous. And for the validator query, we just judge whether the output text is indeed more humorous than the input text, true or false. A trivial model that always answers true will only have a 50% GB consistency. And similarly, we can insert randomness to the validator queries by casting it as a binary choice question and randomize the orders of A and B content. So using the same style transfer example, the generator query is like to rewrite the input to be more humorous, and the validator query will be which one is more humorous, the input or the response. A trivial model that does random guessing will only achieve 50% GB consistency in this setting as well. Now that we've figured out how to generate, how to design the generator and the validator query, the question becomes, what are some tasks that are interesting to evaluate GB consistency on? So here's the table that classify all possible tasks to be the 4 categories based on the difficulty to generate and to verify. Classically, in computer science, there are some tasks that are easy to verify but hard to generate, such as the set problem, like the Boolean satisfiability problem. It is NP complete to generate a solution, but it is polynomial time to verify whether it is satisfiable or not. Inspired by this, we try to focus on the first column, where it is easy to verify, easy to generate, or easy to verify and hard to generate. Because the second column, well, first we doubt whether this thing ever exists. And also maybe it's too hard for GB consistency when things are both hard to generate and to validate. So for example, for the easy to verify, easy to generate category, we think that some classic NLP tasks would fall in here. For example, arithmetic questions, trivia QA like knowledge intensive stuff, or style transfer. And here are some concrete examples. So for arithmetic question, we measure the model's ability to both compute the arithmetic question and also validate whether it's correct or not. Surprisingly, we find that GPT-4 is only 76% GB consistent, meaning that, I mean, the baseline is always 50%, meaning that it's pretty far away from like being 100% consistent. And for trivia, yeah.
What's the accuracy for GPT-4 to generate and to verify separately?
I think for GPT-4 to generate, well, if I remember correctly, well, all the numbers are in the paper. If I remember correctly, for generation, it's probably like around 80%, whereas for verification, it's like maybe 60-ish. So turns out like maybe because it's out of distribution for the model to like answer some validation questions like this, turns out validation prompt or validator side is actually dragging the performance here. So for trivia QA, we measure the language model's capability to answer and validate knowledge intensive questions. And we see that GPT-4 is achieving a pretty good GB consistency of around 95%, whereas and like some 30B models achieves around 80%. Now moving on to the problems that are easy to verify but hard to generate. I think some tasks that fall into this category involve some planning or two conflicting goals. For example, in the Spark of the AGI paper, it includes a subtask called plan arithmetic, and I'll give an example in a minute. So here's an example where we are given this equation 4 times 19 plus 3 times 11 equals to 109. And the goal is to change exactly one integer on the left-hand side so that the right-hand side becomes 52. The question is hard to generate because it involves some complicated reasoning to figure out which number to change. However, it is very easy to verify whether the answer is correct or not because it just involves left-to-right computation. And here GPT-4 only achieves 62% GB consistency because it's easy to generate but hard, because it's easy to verify but hard to generate. And for the task that we call prompt prioritization, we provide two conflicting goals to the model. So one goal is to be consistent with the persona, and the other goal is to still answer the question. So for example, in this case, the persona is an advocate for gun control, and the task is to write a response advocating for something that the persona wouldn't do, like to advocate for the benefit of the Second Amendment. So the generator task is pretty hard because the model needs to resolve the conflict between these two goals, sometimes by coming up with a smart middle ground solution, sometimes by just ignoring the lower priority goal. And the validator task is very easy because it just needs to verify whether the response is aligned with the higher priority goal or not. Yeah.
But in this case, the personas A and B are not both, like they're not both generated based on the generator. So like, could it be that, that, you know, given the output of the generator, persona A is going to be more likely than persona B, even if you ask the generator to give answers that way for persona B?
What do you mean? Oh, I see. You mean like because there are two conflicts, because there's conflicting goals. So maybe the model tends to follow one of them more actively than the other.
Yeah, well, in most in your previous example, the generator was always doing some comparative or was always told to give a correct or incorrect answer. Whereas here it's just told to satisfy some condition.
Yeah.
Condition could be satisfied for both personas.
I see. I mean, like we kind of carefully design the persona so that they are like kind of in contradictory to each other. I mean, for example, like, well, one other example would be like if your chatbot should never give refunds to customers, but it should also try to make the customers happier. It's like overall a challenging task. Yeah. 5 minutes. Okay. Cool. So we'll also summarize the results here. Overall, it just kind of suggests that GB consistency is an effective approach to review some model weaknesses, like GPT-4 is suffering some low GB consistency scores. And knowing that these models are not GB consistent, our next goal is to improve their consistency. And we call our method consistency fine-tuning. Here's how it works. The first step is data collection. We set out, given a set of input question X, we pass it through a generator query to get the generator responses. And then we construct the corresponding validator query and use the same language model to get their validator response. And then we check for consistency between the generator and the validator responses and assign them a label C. Now that we have collected all the data, we filter to only keep examples that are GB consistent and use this data for fine-tuning. And this is the fine-tuning objective. Basically, we take the generator response and question, and we maximize the log probability of generator response given question and validator response given question. So once we finish the first iteration of consistency fine-tuning, we apply the procedure iteratively. In the second iteration, we use the fine-tuned model to collect generator and validator responses. Because the first iteration already makes the model more consistent, we'll just get a larger set of filtered data here, and then that we can use to fine-tune another round of the model. So here's how consistency fine-tuning improves GB consistency. On the 30B model, overall consistency fine-tuning improves the consistency rate by 30%. When we apply the fine-tuning for 3 iterations. And as we improve for consistency, a natural question is, how does it help with model accuracies for both the generator and validator? Because consistency, well, consistent examples are not guaranteed to be correct, because a generator and a validator could be both wrong and still be inconsistent. So GB consistency is a pretty good training signal. It's a pretty good filtering signal for data quality. As we can see here, for example, on the arithmetic task, post-GV consistency filtering, the accuracy for the generator and validator tends to be a lot higher than pre-filtering. Basically, post-filtering evaluates only on a smaller set that are overall higher quality, higher accuracy, whereas before consistency filtering, the overall accuracy is smaller. So this consistency criteria only keeps the higher quality or higher accuracy data. The data we use for the first iteration of consistency fine-tuning tends to also be high quality. And that's why we have more pink dots than orange dots. And after one round of consistency fine-tuning, more data becomes consistent. And because the model learns to generalize from a starting set of consistent examples, and they try to learn to make predictions that are also more consistent. And also because it's trained on slightly higher quality data, it can label more examples correctly as well. So after 2 rounds of consistency fine-tuning, most of the data becomes consistent and many of the labels are correct. So this eventually leads to some self-improvement and bootstrapping for better performance without using any ground truth labels. So empirically, we find that consistency fine-tuning indeed improves both the generator and the validator accuracies by a large margin without using any ground truth labels. So this self-improvement result is pretty exciting. And because now we can bootstrap for model capability improvement by just using consistency as a criteria. Additionally, for the set of tasks where like generation is harder than validation, the generator performance improves a lot to catch up with the good validation performance. Whereas for some tasks where the generation and the validation are similarly easy, we find that the validator sometimes suffer from a higher loss to begin with, like similar to the arithmetic question that you asked. Basically, like this is because maybe there's a distribution shift among basically there's a distribution difference between the pre-training distribution and like when we are asking the model to do some validation tasks. Yeah, right. I mean, roughly to conclude things, I guess, well, I'll just skip some slides. Yeah, oops. Yeah, to summarize the talk, we focus on 2 problems in evaluation. Problem 1 is what tasks do we evaluate the language models on? And problem 2 is like how do we validate model responses? And we propose Olive-Venture and GV consistency to address these 2 problems respectively. I guess overall, it's about using language model with some carefully designed scaffolding to get more reliable and scalable performance. And that's it.
Thank you so much, Lisa, for coming to talk for the PLI seminar. If you have already signed up for the one-on-one meeting with her, I believe it's still going to be in the computer science grad student lounge in the afternoon. Thank you.